All right, so we talked about that. Now let's use some examples, okay? All right, so given the following graph, find the displacement and the total distance traveled on the interval from 0 to 8. So we're imagining this is going to be our velocity function v of t, okay? So if I want to find my displacement, that is going to be the integral from 0 to 8 of v of t dt, okay? So then that would be finding my area under the curve. I don't know exactly what v of t is, but that's okay. I can still find my area. I want it to be opaque. All right, so that would just require me to find the area of both of these triangles, okay? All right, so I would get 1/2 base times height plus 1/2 base times height. Base of my first triangle is going to be 4, and then my height is going to be 2. And then base of my second triangle, also 4, but I have a height of -2. So I get 0. My displacement is going to be 0. Okay. But if I want to find what my total distance traveled is, or just distance traveled, then I need to do the absolute value of that integral from 0 to 8. So then that function would look something like this. And what I would need to do is find the area of those positive values. All right. So the other way you could think about it would be the integral from 0 to 4 of v of t dt plus the integral from 4 to 8 of negative v of t dt. I say negative because those outputs are negative already, so that would flip it and give me a positive value. I'm not going to chase through the area formulas again, but we would look at 4 plus 4, which is going to give me 8 units squared. Forgot to write that with the 0. Okay. All right, questions there? I checked each one of my slides for the phantom graph. I don't think it's there. I think we've completely eradicated it. That's what I get when I duplicate slides. All right, suppose that a particle moves on a coordinate line so that its velocity at time t is given by that function, v of t equals t squared minus 2t meters per second. Find the displacement of the particle during the time interval from 0 to 3, and then find the distance traveled by that particle during that same interval. Okay? Very similar to what we just did, also similar to what you guys did on your quiz as well, too. So if I want to find displacement for part A, I'm just going to integrate from 0 to 3, and I do not need to be concerned with the sign or, whether it's positive or negative on that interval, because I just want to find my displacement. So I'm just going to take my definite integral. If there's negative values, then that'll work against my net signed area, and that's fine. So 1/3 t cubed minus t squared evaluated from 0 to 3. So what do we end up with when we evaluate that? 9 minus 9 giving me 0. Okay. All right, well then let's talk about our total distance traveled, because I'm confident it's not going to be 0. It's clear we have some negative values working against us here. So we should set t squared minus 2t equal to 0. And then we find that that equals 0 where? Take out a t, right? T minus 2. So then at t equals 0, fine, that's one of my endpoints. But then also at t equals 2. All right. So my integral, I need to break up as an integral from 0 to 2 plus an integral from 2 to 3. Where will the absolute value make a difference? Yep, so I need to put an additional negative on that. So negative t squared minus 2t dt. And then the other one I can just let as it is. A couple ways you can handle this. I mean, you can distribute that negative into that value, into those values, or you could also put a negative in front of your integral and then hit it with a negative at the end. Either way is totally fine. I'm just going to distribute it. I also don't need to rewrite it that many times, but it's okay. So negative 1/3 t cubed plus t squared, evaluated from 0 to 2. And then I messed up my limits when I wrote it this time around, but it should be from 2 to 3. One-third t cubed minus t squared, evaluated from 2 to 3. Nope. All right, so negative 1/3 times 2 cubed plus 2 squared minus 0 plus 1/3 times 3 cubed minus 3 squared minus, and then 1/3 times 2 cubed minus 2 squared again. So then we take a second to rewrite all this. Negative 8/3 plus 4 plus 9 minus 9 again minus 8/3 plus 4 which will give me 4 minus 16/3, or I'm sorry, 8 minus 16/3. So 24 minus 16 is going to give me 8/3 for my total distance traveled. Oh, wait, it works in, they give me a unit of measure. So I'm not going to say unit squared. What would be my unit here? Just meters. Good. General rule of thumb, if you are integrating your velocity and then you've got a value, b value here, your units are going to be whatever your units for your velocity are, multiplied by the your linear units, your units for your x value. And then in this case, since it was per second, my x values for my limits were in terms of seconds, so meters per second times seconds just gives me meters. So that'll be my unit of measure. Okay. All right, quick conversation on units and things that, like applications and what they actually mean. So we already talked about this a little bit, but if I integrate my velocity function, velocity is just the derivative of my position function. So we find that gives us s of t evaluated from t sub 0 to t1. So s of t1 minus s of t0. I mean, I wrote this on the first slide. But integrating my velocity will tell me my change in position. Okay, so if I integrate my velocity, what that will tell me is my change in position. Okay. In other applications, if you integrate the rate at which something occurs, what it will tell you is the amount over that interval. So it's another way you can look at it as well, too. So like, if I'm integrating meters per second, the value that I get represents the amount of meters that I traveled during that time interval. And then for acceleration, that's just the derivative of my velocity. So then if I evaluate that integral, that would give me, instead of v prime of t, just v of t from t sub 0 to t sub 1. So what that would tell me would be my, well, I guess I can write it out, v of t sub 1 minus v of t sub 0, which is my change in velocity. So integrating my acceleration will tell me my change in my velocity. Okay. But then just in general, just in other applications, so if we let capital V of t be the volume of some liquid in a tank in gallons after t hours, we could either talk about filling that tank with more liquid, or we could talk about that liquid leaking out of that tank or being drained from that tank or something like that. What would v prime of t tell me? So the derivative of that volume function, what would that tell me? What kind of rate? Because we talked about a couple different kinds of rates. What does my derivative tell me? What kind of rate? Word we haven't used in a little while. What kind of rate of change? Instantaneous. So my derivative tells me my instantaneous rate of change. So this would be my instantaneous rate of change of the volume at time t. What would be my unit of measure? Good job. Gallons per hour. Okay. If I integrate that rate, what will that tell me? It'll just tell me gallons will be my units. What will that represent? So if I integrate it from t sub 0 to t sub 1, good. That would represent my change in volume. Over the interval from t sub 0 to t sub 1. And Ash is right, it would just be gallons would be my unit of measure. Good. All right, well, the final minute we would say this. I won't write this all out. But if P represents your population of a country after T years, P prime would be your instantaneous rate of change at a specific timestamp. So if we let it be an integer, it'd be like an instantaneous rate of change after 5 years, or we could do like 5.5 years or something like that. So then if I integrated that rate, so if I integrate p prime, what would that tell me? Change in what? Population. So we'd say of, whatever we're talking about per years, people per year or something like that. Okay? All right. Day 2 homework is there. You're doing displacement and total distance traveled for 9 through 16. Okay? Tomorrow we'll come in, we'll review that, and we'll do some more 5.6 stuff. All right. Have a good day.